Hello, viewers. In today's lecture, I'm going to cover MIPS instruction set architecture and pipeline hardware. Pipelining technique to improve CPU performance. I started in my previous video, and today it will be in continuation to that. And we are going to take some program written in assembly language which will use the instruction set architecture of MIPS computer. MIPS stands for microprocessor without interlocking pipelining stage, and we are going to see what is MIPS architecture and what is the philosophy behind the MIPS architecture. So, the computers can be divided to belonging to two different architecture. One is called RISC, another is called CISC. RISC stands for Reduced Instruction Set Computer, and CISC is for Complex Instruction Set Computer. In RISC, each instruction performs only little bit of work, whereas in CISC architecture, each instruction performs more work. So, a program will generate more number of instruction in RISC than in CISC, but the time taken will be less per instruction in RISC because it is only doing little bit of work. So, what is ISA? ISA stands for Instruction Set Architecture. So, that means what kind of operation or opcodes are available, what is the instruction encoding and representation in assembly language and in binary that we are going to see, and those the program written in MIPS ISA we are going to implement in pipelining because RISC is a simpler architecture. Instructions are of same length, they all take same amount time, and parallel execution or overlapped execution in pipelining is clearly understood. They are better. That's why we are taking this MIPS ISA example. And we have started this pipelining lecture before, and there we have seen that how pipelining technique can improve CPU performance, how much it can speed up. So this ISA defines the family of microprocessors from the beginning. From 1950s, different computer vendors have defined their instruction set. For example, Intel x86, they have a different set of instruction than Sun Spark and then that of IBM 360, etc. And ISA includes instruction set and rules for how to use those instruction, how to access memory, and how many registers can be accessed in one instruction, like that. So this instruction set architecture is an abstraction for interfacing with the hardware. The hardware is too much in low level, and understanding that is more clear if we see this MIPS ISA getting implemented in a pipelining hardware. So, here we are going to see that the evaluation of different kind of architecture. In 1970s, computer designer used one address architecture. The example given here is add a an address, means whatever value is in that address will be added with the accumulator, and the result will be kept in accumulator register. So accumulator register was implicit, and address is only, it can show only one address. Then in 1980s, Intel x86 computers or microprocessors, they have taken two address architecture. One example instruction code is add EAX, comma EBX. Those are effective address. So here A plus B are getting added, and the result is kept in A. Then in 90s, when things have improved a little bit more, the hardware and the design philosophies also, That time MIPS was designed and it was taking three address architecture at $2, $3, $4. That means this dollar symbol is used to name the register. So $3 and $4 registers will be added and kept. The result will be kept in $2. So this is just how the architecture has evolved, and MIPS is a RISC architecture and it can access up to three registers also. We are going to see other classes of RISC instruction sets. So, what is the philosophy behind risk architecture is that it has low complexity and it generally results in overall speed up of the processor, and it is less error prone because the instructions are much simpler. They do little bit of work at a time, and it generates simple microcodes. And for VLSI implementation also, each piece of hardware, function hardware, they will take less number of transistors. So the extra transistors in a chip that can be used for more number of registers in the CPU or cache memory provision in the CPU. And as the design is simple, reduced design, and the design time is simple and it is less error prone, and it has more edge over its competitors. So these are the benefits for risk feature which is implemented in MIPS computer. So we have seen this execution time formula, that execution time equal to instructions per program times cycles per instruction times seconds per cycle. So in risk architecture, they try to reduce the cycles per instruction because little bit of work per instruction and seconds per cycle. Whereas in CISC architecture, they try to reduce the instructions per program because each instruction will perform more work. So MIPS is the implementation of a RISC architecture. One particular example, MIPS are 2000 ISA, designed to use with high-level programming language. So programming language will be compiled to this assembly code of MIPS architecture, and it will minimize the amount of work per instruction, and it will load, and it is also called a load store architecture because first data will be brought from memory to register in the CPU, then the arithmetic operation can be done there. It is called load store architecture. And in MIPS, because the number of registers are more in the CPU, it has to access the main memory less number of times because main memory access takes a lot of time. So by providing more registers in the CPU, it takes less time. And MIPS instruction set architecture has fixed instruction width, which is 32 bits. And we are going to see how these 32 bits are used to make different kind of instructions. So this is an example of different classes of MIPS instruction. One class is called arithmetic or logical or shift or comparison. Second class is for control instruction, branch or jump, conditional or unconditional. Third class is load and store. That means loading data from memory or storing data into the main memory. And other instruction classes also there, and those all classes are formatted into three different formats: R type instruction, I type instruction format, and J type instruction format. So for R type instruction format, 32 bit of instruction word is divided into six division. The most significant 6 bits for opcode, then next 5 bit is for source register, then for target register, then for destination register, Then for shipped amount, another 5 bits, and the last 6 bits is for function. So opcode and function together specify what kind of instruction is that, whether it is add or it is subtract, etc. And for I type, I also stands for immediate value. Whichever instruction uses an immediate value, like some number, they are kept as a constant value, 24 or 1000, etc. The values that is not coming from a register are called immediate values. So here the 32 bits are divided into four parts. Most significant 6 bits for opcode, then 5 bits source register, next 5 bits target register, and 16 bits for immediate value. So 16 bits is a big number. If a branch instruction is using that 16 bits of branch address, it can branch to a distant instruction. And then J-type instruction divides the 32 bits into two parts, 6 bits for opcode and the remaining 26 bits for some values, immediate values. So here also jump can, in 26 bits, you can specify a even larger number, and the instruction can branch or jump to a bigger distance. So MIPS addressing modes, we can see MIPS addresses register operands using 5-bit field. So this first one is an example of an archetype instruction. Add $2, $3, $4. Four registers are addressed. Meaning of that instruction is $3 plus $4 will be saved in $2. And MIPS addresses branch targets as signed instruction offset relative to next instruction, or PC relative, program counter relative. So the number that will be specified in the offset value, that will be added to the PC value, and that will be the branch address. So one example is branch equal $2, $3, 12. So if $2 and $3 are equal, branch PC will go to that 12 address, PC plus 12. From there, the next instruction should be executed. Then immediate addressing with an immediate value, operand is held as constant in instruction word. Example, add immediate, I is for immediate, add immediate $2, $3, 64. That means $3 plus 64, that will be saved in $2. So, more example, JR $31. This is one example, and J128, another example. So, MIPS addresses jump targets as register content or 26 bits of pseudo direct. So, where it will jump, that can be in a register or it can be an immediate value. MIPS address load store location. So load word $2, 128 within parenthesis $3. So $3 value will be added with immediate value 128, and that is the address from where the data will be brought and kept in $2 register. And 16-bit direct address base register is 0, load word $2, 4092, $0. $0 always keeps 0 value. So 4092 is the memory address from where data will be brought and kept in $2. And indirect address is load word $2, 0, 4. So memory address is in $4, and with that 0 is added, 0 offset, it could be any offset. And from that location in the memory, data will be brought and kept in $2 register. Okay, then so more example, So it is showing that add $2 comma $3 comma $4 is a art type instruction, and dollar add opcode for add is all zero, 6 bits of zero, and function for add is 000010. And in the assembly code that is not shown, no. So this is the assembly code to machine language translation. So and $2 is the second register, so its binary value is 0010, and that is the destination register. $3 is the source register. $4 is the target register. Similarly, for jump ALR $3, it is also another art type of instruction, and opcode for that is all zeros, and function value is 9, and source register is 3, and target register not used here, it is 0. Destination register is 31 by default, which is not shown in the assembly code. Then third example is add immediate $2 comma $3 comma 12. It is an example of I type of instruction because it is using the immediate value 12, and opcode for add I is 001000. That means 8, and RS is 3, source register 3, target register is 2, and immediate value is 12. So its machine language instruction is machine bits in binary representation of the instruction is like this. More example, branch equal $3 comma $4 comma 4. If $3 and $4 are equal, it will branch to PC plus 4. So the opcode is given, and then source register given, target register given, immediate value given. So in binary value, it will come out to be like this. Then store what $2 comma 128 within parenthesis $3. It is an I type instruction because 128 is the immediate value, and this is its binary code. Then jump 123 is a J type instruction, and the corresponding binary representation is given here. So if we implement this MIPS ISA in the pipeline, and then we will see what kind of speed up we can achieve, and what is the goal for this MIPS assembly code. So MIPS goal is to keep the cycle per instruction less than or equal to 1. Usually, some instructions take longer to execute than others, but there is no need to wait or waste cycle time for the slowest instruction. We want to utilize the hardware 100% of the time. So, the hardware is split into different stages, and all stages are made to take same amount of time. If the first stage is done computing sooner, it can keep its value in a register. So in between the stages, there are registers where our values are stored. And when the next instruction, the next stage wants it, it will take it from the register. So this is the pipelining concept. So MIPS pipeline, we will see divided into 5 stages. This is a simple example. So the 5 stages are fetch the instruction, then decode the instruction. That means which operands are needed. Then execute, then memory. Sometimes after computing the memory address, you have to go to the memory to bring the data, and then write back the data in the register file. So these are the 5 stages: F, D, E, M, and W. And MIPS hardware is shown here. So this first one is fetch. It is taking the PC value, going to the instruction memory to get the instruction. Then it is going in the second stage decode, where the where it is reading the register file to get the operands. Then those operands are fed to ALU to do the computation, and the result is going to data memory. This is only needed for load store kind of instruction. For other instruction, this stage is not required, but all instructions take same amount of time, so it will still go through this. And then after memory access, it will go and write back the data in the register file. So this is the data path for MIPS instruction. But we have seen before that this pipeline, usually the maximum speed up is number of stages in the pipeline, but pipeline suffers from many different hazards, and those hazards were due to structural hazard or control hazard or data hazard. And in my previous lecture video, I said that structural hazards are all avoided in modern computers by improving the hardware. Like in the memory, the number of ports are two for two reads simultaneously. This is same for register file also. Register file is also a little bit of memory, right? It is only on the CPU. And then control hazards also we haven't gone through, we will go through it, but there are many techniques to avoid control hazards like branch prediction, etc., etc. Where from control hazard comes, if there is an instruction where there is a branch instruction like branch equal, and then this decision whether the equals are true or not, that takes some time, but by that time the next instruction has been fetched. So if the branch will be taken, so that instruction that is already fetched, that will be flushed, and a new instruction will be brought from the instruction memory. So it also waste the pipeline cycle time. So that's why it is called control hazard. And the solution technique is prediction of branch and reshuffling of instruction, so that the branch decision takes gets some time. So now let's take some example of data hazards. So in data hazards, the neighboring instruction, next instruction has dependency on the previous instruction, and there are three different kinds of data hazards are there: read after write, write after read, write after write. So main hazard is the raw hazard. This one is not a hazard. um, and right after right is also not that serious, which can be avoided. So read after write hazard, here you can see two instructions are there, and they have a common data in register R1. In the first instruction, R1 is getting written, and second instruction is reading that value. But when it will get written, before that, second instruction may want to read it. So that is a problem. So usually pipeline has to stall. But if pipeline has the bypassing or forwarding technique from the execution stage or memory stage, then the stall is not needed. So we are going to see that example here. Here it is the same two instructions, and their data dependency was on R1. So this R1 will be written after this write back, right? It will be available here. So it can be forwarded from here. For that, there is a three cycles of stalls if forwarding or bypassing not used. But if forwarding is used from here, from execute state, then here there won't be any problem. EX R1 will be ready, R2 plus R3 will be done here, and from here it can go to the second instruction here. Okay, so it can be avoided for these two particular instruction. But there is one raw hazard which is called load use hazard, which cannot be completely avoided. So let's see these two example: load word R1 comma 0 within parenthesis R2 and add R4 comma R1 comma R5. So R1 is the common register between the two instruction, and first instruction is load word, second instruction is add. That's why it is called a load use hazard. Now when R1 will get its value only after data access takes place in the memory, then only it can be forwarded, right? So that's why it has to take one stall here. So it couldn't be completely avoided. Even with bypassing technique or forwarding technique, one stall is required if there is a load use hazard. The first instruction is a load word, second instruction is an add, subtract, anything with the data dependency, that is called load use hazard, which cannot be avoided. Now let's take this example. Uh, this is a program of eight instruction, and you can see here it is shown where the dependency is. There is a raw read after write dependency here, but it is not a load use hazard, so no problem. Bypassing can technique can avoid the stall. But between second and third instruction, there is a load use hazard. So even with bypassing technique, one stall is required. Then between third and fourth, no dependency, but third and fifth, there is a dependency, but they are very distant apart, right? So that is not going to cause any problem. Between fourth and fifth instruction, there is a raw hazard, but bypassing can avoid the stall. It is not a load use hazard. And then between sixth and seventh, there is one hazard. This is okay, no problem. This is a right after right hazard, so that is not a problem. Because this is the first one, it will write first. In the next cycle, this one will be written. And then between the seventh and eighth, because the seventh instruction is a branch instruction, so the branch decision will be known only after the execute state here, right? It is the 10th stage, 10th cycle. But the eighth, but by that time, the next instruction has been brought, right? So if the branch is taken, it has to throw away the instruction that has been brought already, and then a new instruction will be brought here only. So total number of cycles needed for 8 instruction is 15, and with two stalls here and one stall here. Okay students, in today's lecture video it is up to this. Otherwise the video will be too long, and I will be covering the rest of the examples in my next video. See you then.